So I'm here to talk to you about quantum performance and the importance for performance, especially as we drive a roadmap to build these systems for the future. Now, we've really come a long way with our efforts at IBM in terms of deploying systems over the cloud. It's 5 years ago, in fact, in May of 2016, where we placed the first 5-qubit quantum processor on the cloud. It had a simple composer for developing quantum circuits, had a nice user interface, and it drove a lot of real interest throughout the community in terms of research and in terms of papers that came out. And today, where are we? Today, we have quantum system ones that are deployed in our Yorktown Heights facility. And over that time, we've seen tremendous growth in terms of the usage of our systems, driving 700 papers plus on our services, and executing over 2 billion circuits a day over the cloud. And that's an important thing. Today, we have over 20 systems that are available online. These range from systems with a single qubit on them all the way up to 127 qubits. And what you can start to see with this page that we have on our services page online are metrics that we point to with these different systems. And we see that as really important in order to explain overall what the level of performance of these systems as they're being built, and to show you the degree to which advancement is happening, the pace at which advancement is happening. Furthermore, we're driving critical strategic partnerships throughout the world. And in fact, deploying these systems beyond even just our New York facility. Even though we have over 20 systems deployed in our data center in New York, just this past year, we've managed to also deploy quantum system ones in Germany as well as in Japan. And soon we've announced partnerships where we will be deploying them with the Cleveland Clinic as well as in Korea with Yonsei University. And these are really critical to drive strategic partnerships to have these localized hubs and build this ecosystems in these local areas. Now, as we proliferate all these systems and drive the performance of them, what's behind it all? We've heard a lot of talks about in terms of the promise of quantum computing. But what I want to break it down to is, in fact, the pure element of computation for these quantum computers, and that's the quantum circuit. It's really the fundamental unit of quantum computing. We talk a lot about qubits, and we talk about like the performance of qubits, but really that's just the unit of information. Instead, what I want to talk about is the unit of the computation, and that's really a register of qubits, how you operate a set of gates across them, perform measurements, and then that leads to further computations that can be even done on a classical computer. And then you run these circuits over and over. But these circuits are what drive quantum computational value and drive a differential for what we can actually achieve with computation in the future using quantum computing and exploiting quantum advantage. And so here there are different forms of circuits that drive applications in, say, simulating quantum systems. So if we're looking at physics problems or understanding chemistry better to drive better materials, drug discovery, all of that stuff that we've heard about. To also algebraic problems where here it's really about handling data with some types of group structure or things in the area of machine learning, driving things like differential equation solving or factoring. And then the third element is search problems. Broadly speaking, these more non-exponential speedups, but still a potential benefit of using these quantum circuits to find polynomial speedups in optimization, in sampling problems, Grover's type of problems in that space. And there's already a lot of work and research being done together with industry to really look at use cases that will exploit these quantum circuits for quantum advantage, including improved simulation of chemical processes for things like catalysts, energy efficiency, for driving better materials, boosting classification of data and machine learning for better predictions, studying physics, right? Things such as condensed matter theory problems or high energy physics problems. Those are those are likely going to be tuned to these quantum circuits formalisms. And then also understanding risk models to perhaps do things like fraud detection. All these different areas are really areas that we see interest and applications using quantum services for running quantum circuits. And so the future really is about how do we build a path to permit the consumption of these quantum circuits. Just in a few years, we've already seen with the services that we've launched over the cloud an exponential growth in the number of circuits that are consumed every day. Right? So just looking back to 2018, we've seen this chart of increasing usage of our services, increasing running of these quantum circuits. We, of course, want to get to the point where we have those quantum circuits that drive quantum advantage in those different application areas. But we also need to find a way to develop our hardware and to develop a full stack that promotes this consumption of circuits to the point that we want to be able to reach a capability of running over trillions of circuits per day later in this decade. And so earlier this year at IBM, we released this detailed development roadmap to chart our course towards that vision, which is that we want to get to a point where there's really a frictionless development and frictionless usage of our quantum services. It's part of a broader computing framework where you might not even need to know about the quantum computing backends or the details of the qubits and the circuits that might be running on them at all. But to get there relies on a lot of different work across many different parts of the stack. From the system architecture in terms of the hardware systems that we build and scaling up those systems in terms of the numbers of qubits and their performance, to middle layers of the software stack of understanding how to drive better compilers, how to have the classical and quantum infrastructure to be more tightly contained in order to speed up executions of problems that are of interest. Then containerizing some of those runtimes into more application-oriented environments, and then further abstracting it at the top level so that users who want to get towards results in their domain of expertise, say in chemistry or machine learning or finance, do have that frictionless interface to actually make use of the quantum services and run their quantum circuits, but perhaps not even knowing that that is going on underneath. And so to realize this roadmap, we need to really have a foundational element of the hardware, right? In terms of driving performance of the hardware so that we can actually chart this path forward. And so what I like to talk about are three key metrics which we can use to measure quantum computing performance. And that's scale, quality, and speed. Okay, so scale is really measured by the number of qubits that you have. It effectively tells you about the size of the circuit which you can run across your quantum processor, that you can run in your quantum system, right? And obviously the larger is better. You can handle more complex problems with more qubits. Quality is about how well those quantum circuits can actually run on your real hardware. There's a metric that we define called quantum volume, which allows us to actually measure that quality of performance, and effectively is dependent on some of the underlying performance attributes of the underlying hardware. And then the third element is speed. And this you can think of as throughput of these quantum circuits through the entire system. And here now the entire system is more than just that quantum chip itself, but it's the full integrated system of the quantum piece and the classical piece, because that's all working together in any realistic problem that we're trying to run. Your circuits involve quantum computations and classical computations, and any problems of interest for practical application require the running of millions, if not billions, of circuits. So let's start by talking a little bit about scale. In terms of scale, we've been embarking on this multi-year roadmap to scale our quantum processors. And here, this really relies on the foundational elements of technology development. And this roadmap culture that we built is very inherent to IBM in terms of our past with driving roadmaps of node development in semiconductors. And so that really was a big starting point for how we envisioned this roadmap of hardware development across these different processor generations. And what we wanted to do was scale, but scale in such a way that every one of the generations that are coming out solve a particular critical technological hurdle. And so a few years ago when we released Falcon, which is at 27 qubits, the key driving element of that was actually yield. Having a precision Josephson junction process that allowed us to really target the frequencies and energies of the qubits that we want so that we can reliably and reproducibly yield devices and put them over the cloud in a stable way. Then with last year, we released Hummingbird. Hummingbird was at 65 qubits. And a big part of that was actually scaling our measurement technique to actually use something called multiplex readout to reduce the total number of readout infrastructure pieces that you have in these dilution refrigeration systems that we use to actually house the quantum processors. And that opened the door to this range of 50 plus qubits. Now, this year with Eagle, and I'll go into a bit more detail in a few slides, is about scalable packaging. As we get to 100 qubits, you have a problem of wiring, especially of bringing wires into the interior to talk to all these number of qubits that we might lay out. And here we rely on our decades of semiconductor fabrication expertise at IBM to develop some of these scalable packaging techniques that work in a quantum environment and in a cryogenic environment. Next year, our target is to build Osprey, which is over 400 qubits. And the key challenge there is to drive infrastructure within the actual quantum computing system in terms of scalable I/O, having a possibility of not requiring all these different kind of coaxial cables that you might have seen in pictures, but to actually have a more scalable signal delivery system. And then in 2023, we plan to build Condor, and Condor is over 1,000 qubits. And there, actually, the problem comes back to developing what are called scalable space transformers, or effectively some of the glue that connects the signal delivery pieces to the actual underlying qubit processor itself. And so here's a picture of our latest generation, which is Eagle at 127 qubits. And Eagle is effectively founded upon these advanced packaging techniques, right? So really using some of these ideas from the CMOS industry, multi-level wiring, as well as through substrate vias are critical to what we have here in order to provide us the possibility to bring over 100 lines to the interior of a chip to actually communicate with all the qubits. And so really having this integrated into this multi-chip stack, where we're not just relying on all the different lines coming on within a single plane, but we have these multiple planes to serve different purposes. We have our qubit layer, we have readout layers, we have wiring layers for bringing in the microwave signals. And really this is taking a lot of things that are known, but making them to work reliably and reproducibly in our superconducting qubit architecture. And so it's as I said, three different layers, pattern dielectrics within. Just a bit more of a detailed view of the cross-section of some of these different layers that we have. And this is a real system. We announced it a few weeks ago at our Quantum Summit. And then since then, we've continued to work on further calibrations to bring it up. And so now what we have here, you can see is the entire device map of this 127 qubit Eagle processor. This first backend that we will be releasing is IBM Washington. And this is actually an important part, right? That when we talk about the number of qubits as a metric, we're talking about the total number of connected qubits with detailed metrics that we can stand behind. And so that means things like coherence times in terms of relaxation times, all 127 of them, with a median of, in this case, 90 microseconds. All the T2 phase coherence times, right? Here with the median of 100 microseconds. Readout errors, right? So we need to be able to know the assignment errors across all the qubits. In this case, a little over 1%. All the different pairs of 2 qubit gates. In this case, still a few of them to come, but most of them already all to be measured here with a median of sub 1% across the device. And so really that's the story about driving scale and where we are today with 127 qubit device. Now, there are other elements also which continuing the story that are critical, right, for driving performance. And here the next piece is quality. Quality really is a metric that we've defined to be measured using quantum volume. Obviously, there are different ways that one can think about about quality, but quantum volume is one neat metric that allows us to use one number to wrap a lot of the different non-idealities that might occur in a system into a roadmap. And so some of the different elements that go into this quantum volume are things like coherence, right? Driving those T1 and T2 numbers. How long does do the quantum states remain coherent in your actual physical qubits? The gate fidelities of the underlying operations, right? So both single qubit gates, 2 qubit gates, readout errors, readout assignment errors, reset errors. And then also things such as compiler efficiency. So here's where some of the software stack does start to come into play too, because with quantum volume, it's meant to be a really hardware agnostic measure where the particular circuits that you might need to run to benchmark this quantum volume might not be best suited for the particular arrangement or hardware array that you have in your system. And so there's some compilation that might need to be done. And so driving better compilers, kind of along the lines of all these other parts of the stack as in the previous talk, are really critical also to make improvements in terms of this type of performance. And quantum volume really is this type of measure that tries to look for what is the best or largest square-shaped quantum circuit that can be run on the real hardware. And at IBM, we've been driving this with a doubling of quantum volume year after year, hitting quantum volume of 128 with our Montreal backend, and then most recently, actually, a number of the other backends that are available over our cloud services also have quantum volume of 128. But also, we are very excited about some of the progress that we continue to make in our hardware to push this even further in the years to come. And a big part of our development roadmap is, in fact, a lot of different parallel generations of work happening all at once. And so we talked about Falcon, we talked about Hummingbird, we talked about Eagle, but all these are all happening in parallel, and we're driving different elements to make it happen, to make improvements. So just in terms of Falcon, which is our 27 qubit vehicle, we've been able to make tremendous strides in terms of pushing things in coherence and gate fidelity. So with our current core processors, which are Falcon R5, the 5th generation of our Falcon processors, we typically have an average of around 100 microseconds of coherence times. We've had a recent generation, Falcon R8, that actually triples that. So median times in the range of 300 microseconds. And then we have other further test devices that show that we should be able to push even further. So medians of 600 microseconds and even pushing to milliseconds of coherence times. Then from the 2 qubit gate front, I like to show this plot because it really shows this kind of agile hardware development and cycles of learning over different generations of devices that we're building. And so this dates back to when we were first starting to put some of these larger devices over the cloud, 20 qubit devices, and the progress of really reducing the gate errors through various different elements, right? From improving things like coherence, from driving things like better gates, better pulse control. And to the point that now today we have a new exploratory system, our Falcon R10 processor, which actually hits below 3 nines of fidelity, so below less than 1 E-3 of gate error. And so those are 2 elements, right? So scale, quality, and then the third one is speed. And speed is really what brings practicality to our quantum to quantum applications. And so quantum computer programming really will require many circuit runs. For certain types of problems that we are considering in the area of chemistry or in machine learning, it could be billions of circuits. And so that means that we need to be able to have a large throughput of these circuits through the actual hardware, both the classical infrastructure and the quantum infrastructure, because they are communicating with one another. And so what determines that speed, right? So at the very core of the quantum hardware, there's how fast can we run those operations? We want to have fast gates. We want to have effectively with superconducting qubits. That's something that's really, really great about the architecture that we have, that these gates can be on the order of tens to hundreds of nanoseconds. You also want to have fast readouts, right? In terms of being able to reset and reuse your qubits for further circuit runs. You need to be able to turn your information to classical bits and then kind of get those qubits back into the system for using again. And we want to be able to bring those times down. And then we need to have that really, really good interface with control electronics in terms of latencies, in terms of how long some of the pulses live before they get generated and are sent to the actual quantum hardware. And then there are elements of the software architecture itself in terms of the assembly language OpenQASM3 to have elements built within, such as feed-forward and dynamic circuits, and as well as containerized environments such as a Qiskit runtime. And so we've also had a major progress this past year in the speed metric with regards to some of the underlying hardware that we have. By transitioning from our Falcon R4 processors to our Falcon R5 processors, we've had a boost of 15 times in terms of the readout time, basically shortening the total amount of time from a few microseconds down to less than 500 nanoseconds for most of the readout times. So having readout on par with some of the 2-qubit gate control times on our systems. And then furthermore, we also now have Qiskit runtime available across all of our systems. And so what Qiskit runtime is really a containerized object for you to have your circuits run in the classical computing side very close to the quantum hardware itself as well. In the past, when we were running quantum circuits over the cloud, you're sending these jobs circuit by circuit, and they need to go to our quantum processor. The results come back to the user. Then you need to decide, for example, in a VQE problem, what is the next thing to do? You're going to send a circuit again. And now instead with Qiskit runtime, we have that all co-located near the quantum processor so that we can actually do a batch of jobs in a much shorter amount of time, bringing down the total execution time for algorithms of interest. And so this makes a big difference when it comes to doing a practical problem, such as running a variational quantum eigensolver problem to look at, say, a lithium hydride curve. It can mean the difference between getting a solution for your chemistry problem in a matter of hours versus a matter of potentially many hundreds of days, right? Depending on the total wall clock time it takes to get your circuits in and out of the system. And so this is really why we are so excited about superconducting qubits at IBM in terms of the potential performance that we can really get, right? And when we're looking at different architectures, this is really important that we look at how they stack up in these different areas in terms of quality with quantum volume, in terms of scalability, right, with the number of qubits that can be actually fully controlled and addressed and benchmarked and characterized. And then from a speed standpoint, right, we define this metric called circuit layer operations per second clops to really give another framework and give another metric in this space for us to actually define this whole landscape of quantum computing, so that we can really progress forward and see that along these different roadmaps that we're driving, that we are making progress as we march forward. And so that's really exciting for us in this past year that we've been able to hit these two landmarks in 2021, both delivering Eagle at 127 qubits and also enabling this Qiskit runtime containerized framework to really speed up circuit runs across all of our systems. And so I'd like to just kind of leave it with that, which is that I think that as we want to drive new capabilities and we want to drive the adoption of these systems to run more and more quantum circuits, performance is absolutely critical. And performance, at least of the hardware, is built upon scale, quality, speed. We need to combine performance with new capabilities, with really with a frictionless framework, so that we really drive towards value for the users in that frictionless framework in the future. And with that, I'll leave you with a few resources for learning more about our quantum systems that are available over the cloud, as well as our open source framework, and happy to take any questions.
What happens after 2023 beyond Condor, and what's the big challenge?
Yeah. So beyond Condor, we want to continue to address scalability, and we're already starting to look at modular architectures, right? So I think modularity is going to start to be key in terms of how we can actually scale either at the package level or at the system level. There are a number of different elements that we're looking at for that, right? But it's very, very important to continue to scale, and there are different frameworks for doing so. Oh, back there.
So Jerry, I imagine when you design the next generation, you always want to improve on all of these criteria, but the reality might be a little bit different. And I wondered whether you could qualitatively comment about, are these things shrinking in area or getting bigger? Are they increasing defects in exchange for scale? Do you have to make trade-offs as you evolve?
It's a really great question. And I think part of that is precisely the agile hardware development journey that we've embarked upon here, right? Like, which is that we have these multiple generations, and they're somewhat intersecting, and we want to bring all the best parts into these other ones, but they all have their own type of independent timescales for it to happen, and they're all happening at once, right? And so making that all work seamlessly is really, you know, the challenge that we've embarked upon. But to that end, in terms of qualitatively, right, like the idea here is that we see no physical blockers on this roadmap to where we want to get to, right? In terms of driving these technologies forward, and that's kind of how we charted the roadmap, which is to overcome each one of those hurdles to get towards that 1,000 qubit level. And you know, we are actively already kind of defining now what are those hurdles for the next set of node points, right? And certainly, I think, you know, size and footprint could become one dimension to look at, right? Especially if you want to try to keep the same chip size. But that's why I'm bringing up also the concept of modularity, where you have the potential to actually still drive coherent quantum links, but in a different form factor, through either packaging or through also other types of more scientific and researchy quantum links.
So it's hi, I'm here. So,
hey.
So hi. So it's on similar vein. So you have different chips which address different quality criteria. You have a smaller chip with higher quality, and you have a larger chip with lower quality. Do you expect any evidence that you will be ever able to bring high scale, high quality in one chip? Because we have yet to see that.
Well, I think the whole point here is that we are driving these different attributes on different generations of our development roadmap, right? And so Falcon, we're already up to 10 generations, and that's because and that's 27 qubits that we've been pushing on improvements in things like coherence, gate fidelity, speed of the readout, et cetera. And Eagle, this is just this is our first Eagle that's come out, Eagle R1, right? And so we expect to continue to drive that as well. And in terms of timelines and where these line up, we had to start Eagle back during basically Falcon R4 days to get here, right? And so, but then we want to reduce these times and then bring more of these quality features into the more advanced the scaled up types of devices as well. And so these are all kind of happening in parallel, and we obviously want all these things to feed up, and we don't see any reasons why they shouldn't.
Thank you very much. Thank you, Jerry.